As I already mentioned, the implicit Euler method requires solving a subproblem at each iteration step. You need to solve an equation, possibly a nonlinear equation, at each iteration step. This incurs some additional algorithmic effort and also the mathematics of those subproblems. As usual, understanding the mathematical background of a computation problem will help us developing and improving algorithms for those problems. Let's briefly review the basics of the implicit Euler method. So we have a Cauchy problem, u prime of t equal f of t u of t, with initial condition u of t naught is equal u naught. And each iteration step of the implicit Euler method works as follows. We solve the equation uk plus 1 equal uk plus h times f of tk plus 1 uk plus 1, where uk is the iterate that we have already computed for the previous time step, h is a step size, and uk plus 1 is now the unknown. This equation defines uk plus 1 implicitly as a solution to that equation, or maybe it's also a system of equations, of course. So at each iteration step, we have to solve a subproblem which constitutes in solving this possibly nonlinear equation. And as you remember, you can also rephrase this as finding the root of a function. By rearranging this equation, you can also write it as uk plus 1 minus uk minus h times f tk plus 1 uk plus 1 equals 0. The left-hand side, as you can see, is actually or can be considered a function in uk plus 1. So solving the nonlinear equation boils down to finding the root of a function. And for that, we already have a variety of tools. Examples include the bisection method or the Newton method. Now, before we rush ahead and implement the implicit Euler method for some ordinary differential equation, we would like to improve our understanding of this mathematical problem. For example, we need to make sure that the solution actually exists, that this equation actually has got any solution at all. If there weren't any solution, we couldn't proceed with the implicit Euler method. And what's more, we also would like to have not 0, not 2 solutions, but only 1 solution. If there were multiple solutions, then we wouldn't know which of these solutions to pick and how to proceed. Also, most likely, if there were multiple solutions for this subproblem at some iteration step, that would probably not be physical, because typically we are interested in ordinary differential equations that have unique solutions. So if the ordinary differential equation has got a unique solution, then also the numerical method should have like a unique trajectory without any freedom of choice. As an example, we consider a particular Cauchy problem, namely u prime of t is equal negative u of t over 1 plus ut squared. And let's say at the initial condition is u at 0 is equal u naught. You can easily check that this equation satisfies the conditions of the global existence uniqueness theorem. So for any choice of u naught, there exists a unique solution for all times. In fact, it should be an additional exercise. Now, the implicit Euler method for some step size h can be set up as follows. The equation at each iteration step is uk plus 1 equal uk minus h times uk plus 1 multiplied with 1 plus uk plus 1 to the square to the minus 1. Solving that equation can be rephrased as finding the root of a function. In particular, at every iteration step, we need to find uk plus 1, which is the root of the function g, where the function g is defined as follows. G of u is equal u minus uk plus h times u times 1 plus u squared to the minus 1. This function g depends on u, and in order to find uk plus 1, we need to find the root of the function g. Before there's any confusion, the function g, as you can tell, includes the step size h and the previous iterate uk as parameters. So depending on the step size, the function will always be different. And even with a fixed step size, at each iteration step, the function g will be different depending on the previous iterate uk. Now we would like to make sure that this function g has a root and that the root is actually unique. To understand why that is the case, let's take a look again at the definition of g. So we have this term u minus uk, which is essentially a linear function in u, and this additional term h times u times 1 plus u squared to the inverse. Now by looking at this last term, we can tell that it is bounded in magnitude, and for h small, it will actually be a fairly small term. So the function g essentially is a linear function in u plus some additional perturbations, so to speak. In fact, at this point, it might be helpful for you to plot the function g for some values of uk and h, just to get an idea of what the function looks like. So in particular, for u very large in the positive direction, we will get a positive value, and for u very much in the negative direction, we get a negative value. So by the intermediate value theorem, g certainly has got a root. Now we need to make sure that the root is actually unique. And one way to do that is to show that the derivative never vanishes. One can check that g prime of u is equal to 1 plus h times 1 minus u squared over 1 plus u squared to the square. That is a simple calculation which is left as an exercise. Now this derivative g prime of u can be seen as the constant function 1 plus some small perturbation. Indeed, just by looking at the last term, 1 minus u squared over 1 plus u squared to the square, you can tell that this term goes to 0 as u goes off to plus infinity or minus infinity. So in particular, the magnitude of that term remains bounded. For some very small step size h, for example, h at most 1 over 10, we can actually check that g prime of u is always positive. So for step size small enough, the derivative of g is always positive, so the function g is steadily increasing, and so the root of that function, which we know exists, must indeed be the only root of that function. If the function g assumes the value 0 at some point, then the positive derivative forces it to grow further without ever assuming 0 again. Okay, now that we know that g has a unique 0, we know that the equation of the implicit Euler method has got a unique solution, and so we can, for example, use the bisection method or the Newton method to find the root of that function g. And again, that additional computation has to be done at every iteration. There's a very nice theory that helps us to understand under which circumstances the nonlinear problem in the implicit Euler method has got a unique solution. In fact, the mathematical background of that theory will also provide a numerical method, a computational method, to obtain the solution to this nonlinear subproblem. We can approach the solution theory of the nonlinear problem in the implicit Euler method by fixed point theory. Fixed point theory is a branch tree analysis which is concerned about mappings and their fixed points, which means points that these mappings map to the points themselves. In our case, let's take a look at the mapping phi of u, which is defined as uk plus h times f of tk plus 1 u. So u is the input variable, and the output is uk plus h times f tk plus 1 u. This mapping is just right inside in the defining equation of the Euler method. Now every solution of the equation in the implicit Euler method is a fixed point of that mapping phi. If uk is the solution from the previous iteration of the implicit Euler method, and uk plus 1 is the next iterate of the implicit Euler method, then we see that phi of uk plus 1 is equal uk plus 1. In other words, any solution of the nonlinear problem at each iteration step of the implicit Euler method is a fixed point of this function phi. And before there's any confusion, phi of course depends on the current iteration step. U is the input, but u of k and the step size h are parameters of this phi. Now, having observed that we can characterize the solution as a fixed point of this function phi, can we in some way use fixed point theory from real analysis to understand the solution properties of the equation? Does real analysis even provide us with a solution method that we can use in computations? One fact that we're going to use is that this function phi is a contraction, provided that the step size h is small enough. So let's assume that f satisfies this continuity condition as usual. Namely, we assume that there exists a non-negative number L, such that for all u and v, we have that f of tk plus 1u minus f of tk plus 1v in Euclidean norm is bounded by L times the Euclidean norm of u minus v. One consequence is an upper bound for the distance of phi of u and phi of v. Namely, the Euclidean norm of phi of u minus phi of v is just the same as h times the Euclidean norm of f at tk plus 1u minus f at tk plus 1v. And now using the continuity condition on f, we have that this is bounded from above by L times h times the Euclidean distance of u and v. Something intriguing happens if h is small enough. More precisely, if h is smaller than 1 over L. Because then we get that the Euclidean distance of phi of u and phi of v is strictly smaller than the Euclidean distance of u and v. In other words, if I take any 2 points, u and v, and I apply the function phi to these 2 points, u and v, then the image of these 2 points will have strictly smaller distance than the 2 original points. In other words, phi is a contraction because it contracts the distance between 2 points. These two facts together, namely that the solution u is a contraction of some mapping phi, and that this mapping phi is a contraction, allows us to apply a very powerful tool from real analysis. The tool I'm talking about is a Banach fixed point theorem. The theorem goes as follows. If phi is a mapping from R to the n to R to the n, which satisfies that for all u and v from R to the n, the distance phi of u minus phi of v in Euclidean norm is bounded from above by q times the distance of u and v, where q is some constant strictly smaller than 1. Then there exists a unique u star in R to the n, such that phi of u stars equal u star. In other words, u star is a fixed point of phi. So any mapping from R to the n to R to the n which satisfies this contraction inequality for some parameter q that is strictly less than 1, we have a unique fixed point of that mapping. Moreover, if I've got any u0 in R to the n, and then define recursively u1 is phi applied to u0, and u2 is phi applied to u1, and u3 is phi applied to u2, and so on and so on. If I define the sequence by repeatedly applying phi, then in fact the sequence converges to u star. So if I keep applying phi over and over again, then the results that I get are going to converge to that fixed point. And fortunately enough, this theorem, the Banach fixed point theorem, applies to our setting. Now let's assume that the function f satisfies our usual continuity condition, namely that there exists L non-negative such that for all u and v in R to the n, the Euclidean distance of ftk plus 1u and ftk plus 1v is bounded from above by L times the Euclidean distance of u and v. Under those assumptions, the equation uk plus 1 equal uk plus h times f of tk plus 1 uk plus 1 has a unique solution, uk plus 1, whenever h is strictly less than 1 over L. Furthermore, that unique solution can be obtained by the following computational procedure. Namely, I take any starting value, uk plus 1, 0, in R to the n, and then I compute uk plus 1, 1, being uk h times f tk plus 1 uk plus 1, 0. Having obtained uk plus 1, 1, that manner, I compute uk plus 1, 2 equal uk plus h times f tk plus 1 uk plus 1, 1, and so on and so on. And that sequence of approximations of uk plus 1 is in fact going to converge to the true solution uk plus 1. For the sake of practice, let's briefly prove that the Banach fixed point theorem allows us to such a conclusion. Namely, we define this mapping phi of u equal uk plus h times f tk plus 1 u. And then, okay, for all u and v, we find that the Euclidean distance of phi of u and phi of v can be bound from above by L times h times the Euclidean distance of u and v. And, okay, L is some constant which only depends on f. And if I choose h so small that L times h is smaller than 1, then just by definition, phi is a contraction. And so the previous theorem is just a simple conclusion from the Banach fixed point theorem.